That's a very clean, very nice way of thinking about gravity. You have an acceleration field. It doesn't depend on the particles themselves. It's just caused by the matter. If you place an object, a particle, in that field, it will accelerate according to the value of that field. Now that obviously is a vector field, because at each point it has a magnitude and it has a direction. So you have a vector field in space. And it tells you also that this is a property of the medium. Gravity, the ordinary gravity that we spoke of earlier and you learned kind of in high school, is a vector field that is a property of the space. It's not a property of the particles falling in. It's given rise to by some matter. You have this field in space, and it's a vector field. Now, we've rejected that. We throw away that model. No, gravity is not a vector field in space. It still is a property of the medium. It still is a property of the space. But it's not this vector field. Because what it has to describe are these interesting relative accelerations. So instead of having a vector pointing in a certain direction, we have something that points kind of in a double-edged way, up in both directions like this, up, down at the same time, and in. So at every point in space, in every region, what this tidal field tells us is what would happen to neighboring inertial particles. If you put neighboring inertial particles here, they would have these relative accelerations. So that's a complex kind of mathematical entity to describe all that. It's not describing one acceleration in a certain direction. It's describing a bunch of different relative accelerations. It's not a unique directionality, so to speak. And that turns out to be a tensor. So the tidal tensor is what describes mathematically all this effect. So now we have a model of gravity that tells us that in the vicinity of matter, there is a tidal effect on the space, and it's described by a tensor.